Hello everyone. Today we cover the topics that are continuation of the previous set of lecture series on transformers, on self-supervision, pre-training and post-training. So the topics that we will go into today are related to test time scaling, model compression, diffusion and benchmarking. So together with the previous topics, these form the full set of topics that we want to cover on deep foundation models, in particular large language models, their training, evaluation and testing for multimodal data content. Right. So, what the first few topics I want to get into are aspects related to test time scaling. Right. So, models are trained, models are available, and then we want to further expand their capabilities to certain tasks, certain domains, certain modalities that they are not extremely comfortable with, and then increase and improve their capabilities. So, to remind one more time, what are test time scaling methods? So, test time scaling methods are those where we try to keep the model fixed but allow more compute at inference, allow more cycles of inference, more tokens, more search, more samples, etc. at the inference time to improve your response. So, many of us are consumers of many of these models, and if you start using some of these models in today's series of model releases and so forth, you will start seeing options like fast, you will start seeing options like flash, you start seeing also options like thinking, extended thinking, deep research and so forth. So, these are different variants of how much test time scaling you allow. Right? If you allow very little to no test time scaling, you get instant immediate responses. If you allow significant thinking and search, then you get nuanced, very refined, very relevant responses, but with higher latency. Okay. So, in this particular subset of topics, again the topic is diverse and vast. We are going to pick up a small subset of these that relate to aspects of chain of thought. So, once I go into, before I go into discussing what chain of thought is, I thought it's a good idea to at least start describing what we mean by thought, right? Our thoughts about what we define as a thought could be varied. So, for a model, what do we define as thought? So, it's a partial plan, right? In a modeling setting, what we mean by thought is a partial, a step towards the final goal, a partial plan, an intermediate step, a next move. If you think of, let us say, a thought in the game of a chess, it is your next move that you do, could be considered as a thought. If you think of a mathematical problem that you want to solve, if you think of a coding problem that you want to solve with your large language model, then these are immediate steps that increasingly move you towards your final goal. A partial proof of that sketch, a partial step in your derivation, a code snippet or a function that moves you in the right direction could all be considered as a thought. So, having this in mind, we will start reviewing some works that have pushed this so-called frame of chain of thought. Right. So, one of the first works came from Google team. It's almost as old as about 4 years from now from a team from Jason Wei and others. So, what do they talk about, right? So, these are even predate, some of them even predate this so-called chat GPT and this very large language modeling eras. These thoughts and these ideas, I should say, were more in place even with earlier versions of GPT, right? And then when the large language models evolve, these methods are also continuing to evolve and improve. So, suppose let us pick up what we mean by a chain of thought prompting. So, in a setting of standard prompting for a large language model, you might ask a nuanced, a mathematical reasoning based question of having, say, a count in this case, but there are multiple arguments that change this count, right? So, initial presence of 5 tennis balls, then 2 more cans, and then some arguments about what cans might contain and so forth. Now the model has to respond what is the number that you finally have. So in a standard response setting, you just give the answer question and then you ask the model for the response. But in a chain of thought, you can say that you are inducing this manually, right? You don't want the model to respond directly. You are forcing the model to take a step-by-step approach to the and final answer. I mean, I think of this a little bit that when I am also with my kid who is in his 4th grade, many times, oftentimes there are mistakes made in mathematical questions, then we force them, do all the steps, write all the steps. You may know it, but I want to see it. And then suddenly when they write the steps, they start changing the response, the final answer, right? Which happens to all of us, happens to models too. Right? So when you start forcing the model to generate the intermediate steps, right, then the model stays the arguments, right? How many balls did the initial situation possess for Roger? How many balls did he have? Then later on, what was the buy? And then if you have another question about apples, how many were initially there? What is it that intermediate step gives us this count, and then the final step, and then eventually the model gets it more reasonably right. Now let us start making this a little bit more formal. That was the big picture of what a chain of thought is. So what is it in a formal setting? Suppose I have a mathematical problem of this nature that I want to map an input prompt, a question, to its output, say y. And now the chain of thought can be considered as a problem of splitting this mapping into a series of steps, right? So you have your input x, and at every step of the model's generation, you have one of these intermediate reasoning steps. You call it, say, Ri or Rt, and this sequence, you actually do not force it to any number of steps. You let that also evolve. You just force the model to provide sufficient reasoning responses. So every time a response is generated as an intermediate step, you also use the input plus that generated response to now further generate a new response or a new reasoning step, right? So an example is given here. So you give the question and you ask the answer, but you also say, let us think about it step by step. Let's not go to the answer directly, go through step by step, elicit these steps in the response so that it is interpretable and you can explain what the model is doing and what it's not doing, plus it also gives you a better final answer. So it, in 2 ways, it is beneficial. One is that you know what steps it is taking, whether the thought process towards the final answer is correct or not, and if you want to intervene at any subsequent stage where it may be lacking, this gives you that pointer, and B, your answer is also going to be better. So in a mathematical setting, of course, these papers also go into more depth of proving some of these things. I'm going to not get into that level of detail, but what I will say is, in a setting where you want to map from x to y, a direct response generation may have the model stuck in a tiny class of realizable functions. So remember that we want the transformers or these LLMs to realize certain underlying mapping functions, right? In this case, you ask a bunch of arguments and they have to put all those verbal arguments into a mathematical expression and generate an answer. So that conversion of English to a math to a final response is a function, and when you have a direct response, many times the model can get stuck in a tiny class that is realizable. But when you allow chain of thought prompting, where you are now saying every step is a generation of a partial response, you now polynomially increase the number of pathways, the number of realizable functions, right? You are allowing more freedom to search for the right response. So every time you're giving a partial response along with the prompt, then the model knows that, okay, this has already been partially computed and it only has to compute a smaller class of this function or a smaller complexity of the function that it has to do, and therefore it is more efficient, and then you can build this towards a set of or a chain of such steps to get you the right response. It certainly increases the interpretability of the results, right? Every step allows you to know where the model is, what is it getting right and wrong, and so forth, widely used, right? But we can already see what is the disadvantage or the pros and the cons of this approach would be that now you have to run more inference cycles. Now you have to spend more time, more computational effort to get the response, right? So you have to also, therefore now some models also allow this to be automated, but some of them allow you to give that manual control. So you have upfront some understanding of what is a complex response that you are expecting from the model. Should I allow test time scaling and in particular chain of thought, or can I directly go get a response? So if you have a lot of such questions to be solved and they are relatively easy, you probably don't want to invoke the chain of thought because you are going to spend more computational cycles. So just extending this whole approach further, in a chain of thought, you have only one set of choices of reasoning steps, right? Now you can start thinking that when your problem becomes even more complex, for example, I am asking you to write a code to solve a Sudoku puzzle, right? So you have a graphic and now you have to basically write a set of rules and form a set of functions to satisfy all the constraints and then get to solve a given input. To do that, there may be multiple ways, there may be multiple lines of thought that you can form you can construct in the form of a tree, and each path is still a valid path. Some of them might not give you fully the final answer, but they are still exploratory paths that let you move in the direction of the solution. So tree of thought is essentially an expanded set of chain of thoughts, meaning now you can pursue parallel chains of thought. You start with, let us say, certain choices at certain level of the tree. So you say that R1 is the first step, but after the first step I have an R21 and an R22, which are two parallel steps that I can pursue. In this case, these are denoted here, and then you can now pursue independently those two, right? If your compute allows you, you can now parallelly do two lines of thought, two chains of thought, and then go to the final solution. And sometimes an automation can be done when the final solution comes in, which one to pick. Sometimes the models themselves are confused, and some of you, when you use it, the model suggests you two sets of responses and asks you to pick, right? Because equally compelling responses were generated and it lets that choice to be with the user. So when you have complex problems, tasks to get solved, tree of thought prompting is a lot more valuable. Again, further increasing the computation, further increasing the latency, but helping you solve more complex problems. So let's quickly summarize, right? What is a difference between a single chain of thought versus a tree of thought? So in a typical setting, a tree would have branching, would therefore have multiple candidate paths, right? So one path that gives you one solution, but if you have multiple paths, then you have to go through multiple solutions. And you may also require, in some cases, an evaluator, so that certain paths, when the tree takes up, they are not going to even generate the right response. So an agent, a smaller model, can act in parallel to this setting to keep evaluating whether the steps are relevant to the prompt that is asked. If you remember the previous slide, I had a choice saying, or I had a comment saying pruning. So these are situations where an evaluator decided that this tree has digressed too far away, that there is no viable path to come back to a relevant response. So a generator and sometimes an evaluator to allow you to constrain the tree in a meaningful way. You could certainly have lots of algorithmic ways to implement these trees, for example, a depth first search, a breadth first search, beam search, various other sampling methods, Monte Carlo methods, lots of literature on how to even form and prompt a model to go behind these tree formations, right? And certainly the key piece where the tree of thought excels is here, right? So it basically allows you to recover any errors you may have made in your assumptions. So if you made a wrong assumption in the beginning or the early part of your chain of thought, the sequential processing will never allow you to recover from that. But if we have parallel lines or chains of thought, then you can come back and rectify your concerns. So of course then this is the downside, right? You have to pay more for your compute. You have to pay more for the number of calls that you make. You have to make time also for this. One is the computation, other one is the time that you have to wait for a relevant response. So that is pretty much all I wanted to talk about in the chain of thought, tree of thought setting. For the test time scaling. So the next approach I also wanted to talk about, partially relevant to this, but a much more nuanced version of chain of thought, which is to allow you to do a search and retrieve and then generate the response, right? In short, a very well known method called RAG, or Retrieval Augmented Generation, right? So the key ideology, again the big picture, let's ponder more, find relevant documents or information, find subsets of knowledge bases that are relevant to this particular response and then make the decision, right? So again in a high level, two parts, a retriever which basically takes your prompt, identifies from a corpus, a knowledge base, some subset of documents or information sources very relevant to this response, and then uses that along with the prompt to generate the final response. So this key point, will come back to it again, which is that you do not go after the response directly, but you provide more context, right? Even if you remember the previous test time scaling approach, the chain of thought, even the tree of thought, you can think of the final response generation having the context of the response or the prompt plus the previous responses, right? So here also we are talking about adding this extra context, but a slightly different way. It is not just by the model's inherent ability, but by a separate agent or a model that allows you to find relevant pieces of information. So let us make this formal. I'll also give maybe an example at in the rest of the slide. So suppose I have a corpus of the documents. Okay, so this corpus also in some cases is not well defined, right? So assume for now that there is, let us say, a defined subset of documents that you have. Say for example, I am asking a question about what is, let us say, the premium that I have to pay for a life insurance policy from the government of India or from a private entity with so much coverage, with so much, let us say, other choices that I want to make. Then the model has to first understand that this is a query related to an insurance, this is correlated to India and Indian insurance and life insurance and government based insurance, and it has to talk about the premium part of it, not necessarily the claim processing, not necessarily, let us say, the customer interaction and other aspects. So then it has to go pick a set of documents that might contain information about this, and this could also, the documents could also be website resources, right? You can search in the web what are the potential web resources that are available to respond to this particular query. Now some selection has to happen, right? So the corpus, the World Wide Web, if you want to mine from World Wide Web to retrieve the relevant information, they may be huge, right? Now you have to potentially pick a very small subset, because obviously you can't put all of them into the context to generate the subsequent generated output. So some sort of a selection is done. We'll talk a little bit about a very simple way to think about this, and then using this you also append them to the original model or the original generator framework, and then generate the output response. So one more time, the generator has access to all the relevant information, and intuitively, why does it work, right? If you think, let us say, a large language model has been learned at the scale of World Wide Web, it should have seen documents related to life insurance. It should have seen documents from the Indian government's website on policy of life insurance. Why does it need to further go and check on the same set of resources that it saw during its pre-training or its fine-tuning? Turns out that because the scale is so large, this selection and formation of the smaller subset refreshes the memory, right? So in the modeling space, if you think of insurance and others are abstract concepts, talking about very specific things like Indian insurance, like life insurance in India and so forth, becomes very specific. So it has to refresh its own memory and incorporate this. The other component is information and knowledge is constantly getting updated, right? So for example, I could go and ask today morning or yesterday saying, why is it suddenly become very cold in Bangalore, right? Some of us have faced this, and turns out that I could have done it, I didn't do it, but I start reading the news today saying that there is a cyclone in some part of the eastern part of the country, right? So now a model, now if I ask a question of this nature, suddenly why is it cold in Bangalore? It was not part of its pre-training data, it's not part of its fine-tuning data. This is totally new information I want to access right now. So absolute requirement that it has to go and search for the relevant resources of Indian meteorological data, Indian weather data of the current nature, and then use it to provide, right? So it's nowhere in the memory, but still you want the information. So such test time scaling, for example, was not available in earlier versions. So some of you, if you had used earlier versions of models like ChatGPT, it would have even, you would have seen responses saying that my model was trained only with information up to September 2023. Now you are asking new information which I don't have access to. Sorry, I am not able to respond, right? So now this has all gone away because you have expanded your RAG systems. So let us put a very simple mathematical notion, and many implementations are going to be much more complex than this, but to just drive this philosophy in, assume that the retriever is a sampler from some sort of a probability distribution. So what does it have? You have given to this retriever the input data X and a set of documents D, right? So this is your data set, this is your prompt. Now you have some model that has to learn how to retrieve, right? That is parameterized by this theta. So some model that has been trained to learn. And if you want to be very simplistic, you can just say that you just encode the query in this case, which is your prompt, and the documents in this nature, right? So HI is the encodings of your documents, HQ is the encoding of your prompt or query in this case. In the most simplistic form, you just compute similarity, right? How much is the query relevant to the document that you have, and you just rank them, right? You pick a top k. Again, the k size is a hyperparameter. If you have a large enough context that you can give for the subsequent modeling, you can pick a large k, so that even if the similarity matrix is a little bit flawed, even if your encoder to get these embeddings is not very semantically rich, you can get away with errors, false positives in your similarity output. But if you have a constrained model, but if you want to make faster responses through the final generator, you are optimized on the compute side, then you keep a small value of k living with the error that the retriever makes. So what does the final optimization look like? The final optimization then has two pieces, right? We need to generate the response y, right? And that is essentially your model, your LLM parameters, say phi. You also need to provide this z from a distribution from the retriever, and you have to go through all the retrieved outputs in an ideal setting, but in a practical setting you will limit that to a top k and say that the distribution only has k support, and you kind of zero out the rest, right? Then you basically have over the support that you have, you can also assume uniform distribution on the support. You then primarily are looking at doing this in a two-stage way, meaning you have a retriever, it has generated you a set of Z, which are your relevant documents, you append them to X, and now you perform the optimization of the LLM, the phi parameters, to do this in a simpler fashion. There are methods which also do a joint optimization of it. It is incredibly computationally expensive, but you can do, right? You can train models along with the retriever and the generator jointly. So you may ask then, why should it help, right? Again, this comes back to it. Again, if the knowledge information was already present, again, you know that, let us say, I am asking a question from the same training data. Assume that your information was well before the model training happened. Why is it helping? So we already saw in our first session on transformers and in context learning, LLMs are nothing but transformers with additional parts. They are good at in context learning. They are good at learning on the fly. They are good at forming relationships along with the query itself without having precise definition of tasks beforehand. Right? So now, by providing these similar documents, examples, and concatenating them with the query, you are allowing an in context learning. You are allowing them to learn through the context. You are providing a method to locally adapt. If the task is not very similar to what you have learned, you can essentially do the adaptation of this, right? So in this local adaptation setting, I do not know whether some of you remember, this was about a year and a half, where Google had shown that using RAG and using a long context as input, you can extend to tasks that you have completely unseen during training. So for the example they chose was picking an African language which was extremely sparsely used in speech communication or textual communication, spoken by a small population, perhaps only small resources exist. In fact, the Google team showed that if you wanted to translate from English to that African language, the only resource available was a local translation book, right? So the model training had never seen this African language. In the context, the team showed that using the model along with a translation book, right, purely about 200 to 300 page book, that tells how to perform translation, how to learn the language, just in the context and by prompting it to perform translation, the model learns to adapt its general translational skills to translate to this particular pair of languages that it has not seen. So, complete adaptation through in context learning. So, again the mathematics you can say is that when I do the RAG, the final response is this joint probability, right? You are marginalizing over all Z. And if the Z is relevant, means the Z, the documents that you have generated and provided as context, right? Now, what happens is if you think of Py given X comma Z and compare it with Py given X, one can define what is called an entropy or an uncertainty of such distributions, and additional conditioning. The property of the entropy or the uncertainty is that the conditioning only reduces the uncertainty, right? The uncertainty of the conditional y given x and z is less than or equal to the uncertainty given y of y given x, right? Once you prove, once you know this happens, the only case when this equality comes into place is when z and y are completely uncorrelated or independent, right? If z and y are independent, then there is no new information added in prediction, so there is equality, right? So, in the worst case, right, the uncertainty is as good as not having the z. When we modify this to the RAG setting, in the worst case, the model has to ignore all the contextual documents you have provided and just respond to the query. Let's say the worst case is that the retriever completely failed. It pulled out random information. I was asking for weather in Bangalore, maybe it pulled out the weather in LA or weather in Boston and added it as a response. In an ideal setting, the worst case, it should be able to ignore that and generate the response. So, what one can prove then is the uncertainty of the outputs reduced with RAG, the confidence which is typically inversely proportional to your uncertainty increases. You are more sure about the response that you want to make, and therefore your responses are also going to be likely better. Okay. So, that is pretty much the set of topics I wanted to cover on test time scaling. In the interest of time, I will take up the model compression as a small subset of topics, and then we will take a short break for taking up any questions. Right. So, model compression then, why do we need it? Right. The first question we want to ask, because large models are large. Right. So, there is no reason to further motivate them, but there could be certain specific purposes why you want to apply compression, right? While you can largely say that LLMs means there is large already implicitly there, why do I need to reduce that? So, you could be operating in a reduced memory, reduced context length setting. You could be operating in a regime where latency is an issue. I can put in very large models. I don't have compute issues, but I want the response to be very quick, right? So, in some cases we are also involved in certain health projects, right? So, if a health project is running and then a question or a response is asked from a model, the model is going to take 2 to 3 minutes to give you the response, the patient is gone, right? Do you want to say wait, the model is still churning its result, we are going to tell you whether you have a particular condition or not? In many cases that is not a feasible thing. So, latency and throughput, at least you want to get some response or some decision out in some cases to make you wait for a better one, right? So, latency and throughput you absolutely have to optimize in some cases. Cost, many cases this is the key concern, right? If I extend my thinking, if I allow more cycles of compute, I run out of my budget, right? I might get better results, but I don't have the money to do it. Last but not least, many cases we want the models to remain internet free, remain on the device for privacy reasons, for security reasons, for reasons where connectivity is an issue, right? You want them to be deployable in a phone. And if you want to push a model, a large language model onto a phone, many times you need a compression of the large model. So we are going to again talk about very simple things, and there's a lot more aspects related to compression that are evolving, lot newer ideas on this. But among the simpler ideas that we want to talk about, the simplest one is just have the model and prune off the bits. You take your model, the model weights are there, the biases are there, you have maybe an int16, a float representation of the bits, you just cut portions of the bits and make it smaller. You are essentially approximating the numerical resolution of every weight and bias, right? Very quick, right? This can be done with almost nothing, no training. You just have the model, you say that I cannot store 30 billion parameters, I have to make it 5 billion. So ensure that all the bits that you have comes down to reduce this size to an int4 or something of that nature. There is also the GPTQ, which is a GPT quantized model response. There are models like mobile versions of various large language models, which are purely just a bit level compression. The difficulty though is, it is often unpredictable. When you cut off the bits of every weight and bias, you don't have full control. Sometimes they can affect the quality, sometimes they can push the models into responses that they were never trained to do, right? So safety alignments could fall apart, models quality could fall apart, task specific skills could fall apart, modality wise it can hurt certain modalities a lot more. Maybe image understanding is difficult with small number of bits, whereas text is fine. So this kind of things one has to carefully calibrate, understand them, otherwise this is an uncontrolled process. So then people ask questions, what can you do better, right? Now do I have to basically take off every weight and bias and then reduce the bits, or can I do something better, meaning can I look at the magnitude of the weights and biases and then look at certain branches of the model which are low in magnitude and prune off those branches of processing itself, prune off certain attention heads if you want to think of, because the entire attention head and the contribution in the forward propagation is very minimal, so you can quickly throw them off. Again reduces the number of floating point operations, but it again is difficult to judge the impact. Not necessary that a low magnitude means low relevance in the output generation. It is not necessary that the magnitude is the deciding factor. And it also causes unstructured sparsity, meaning certain layers, certain subsets of the model, parts of the model become very sparse, certain layers become very dense. So it is also not necessarily a good direction if you are careful in your responses. So then the two techniques that have a lot more in this direction, a lot more success in this direction, one is very connected to our discussions on LoRa. Right? LoRa we talked about in terms of model adaptation. You can also use it for model compression, meaning every weight matrix that you have, you can approximate it with a low rank representation, which means that now I have to store only and compute only through the low rank matrices. You can computationally generate the output matrix multiplications in a much faster way. Right? You can use your matrix libraries to perform this low rank computations much faster, and the model is cheaper in terms of compute. It's also, if you are going to do that kind of an adaptation tool later, it's also in the right direction, that if you apply a low rank approximation and then a low rank adaptation, they go better hand in hand. But this now requires you to go into every layer, every query key value matrix, every head of every layer, and perform some sort of a decomposition and generate the low rank approximations. Again, it's not very clear how each of those matrices, when you reduce the rank, how they affect. Right? So you also need to perform some calibration, some validation on the low rank approximation. And among all these steps, perhaps the most successful one is what is called a distillation approach. You just do not assume anything about the bits, the magnitude or the factorization aspects. You assume that this is yet another model that you can approximate the larger model with, right? So let us quickly walk through. There are a bunch of blocks here, not planning to go all through them, but assume that the key piece is that there is a large pre-trained model, right? You have trained, you have a big model, you know that it does some of the things very well. Now we want to perform some sort of a knowledge transfer. You design a model that fits into your budget, be it your computational budget, memory budget, cost budget, whatever that is. You design that yourselves, and then you say that I want to approximate the input output behavior of the large model on the set of tasks that I care about. Right? So the setting that I mentioned where I want to use it for healthcare applications, a chatbot for healthcare, I don't have to answer questions about, for example, what is the distance between Bangalore and Chennai. Right? This is a question of general factual knowledge that a health chatbot need not be aware of. While a general large model has to know many things, I can prune it to a subset of tasks that I care about and use that for the transfer. Right? If I want the model to be specific on health queries and responses to that, I don't need to understand geographical distances. I don't need to understand various other geopolitics and so forth. Right? So this kind of thing, you decide what is the task that you want to approximate, you design that task, and then you pick that training data for the student model which you have full control on and perform this teacher student distillation. So of course for this, let us say health queries, if you have a subset of data, then you know the ground truth for that data also. We also know the behavior coming from a large model. Now you use the join loss. You take the loss which aligns the small model with the large model. We also take the loss of aligning the student to its expected output. Right? Purely if you are going to do the expected output itself, then you don't need a large model. You're not trying to approximate the behavior of a large model. Then people have shown that it is not as good. Right? Allowing it to distill, understand some behavior of the large model is almost always beneficial than not having this. Right? So instead of training a small model from scratch on the data that you care about, you distill it, and the distillation allows you more for the same amount of training data. Although you are spending more compute, right? You have to inference the large model, you have to generate partial or full responses from the large model and get them to align it. Right? So the total loss, of course, there is also a control on this. How much is the total loss contribution coming from the teacher model? How much is it from the ground truth labels of the training data used in the student model? This is a hyperparameter that you control to ensure your small model remains frugal about its responses. Okay. So quickly a summary on the knowledge distillation, perhaps the most effective setting. Entire model is trained and the student model is typically much smaller. That's the reason why we want to compress. And on the tasks and on the data that you care about, you have somehow controlled the behavior. Right? So you have better control of how the model behaves on that subset of the task that you are interested in. This is the key advantage. Then of course the disadvantage is twofold, at least twofold. It adds cost. You have to train, you have to spend compute cycles, spend cycles both for inferencing the large model as well as training the small model, and certainly you are going to lose something, right? You can't approximate all the skills of a large model onto a small model, right? If that was possible, then we wouldn't be even talking about large models, right? If everything could have been done in a small modeling space. We are going to lose on generality, we are going to lose on certain skills in traditional machine learning itself, and in, of course, very relevant to this also, the concept of forgetting. the concept of catastrophic forgetting and so forth is relevant. So, how much of it you want to control? Do you want to have a representation of some of the skills that you still want to preserve? Can you create data that is a mixture of the new tasks plus some of the old tasks that you still want to preserve in this new setting and so forth are very, very key design choices. I thank all of you for your attention.